Hello, my name is Margaret Vanato. I welcome you to today's workshop on power analysis for social science research by Denis Cohen and Alexander Wenz. The Social Science Data Lab is an event series at the Mannheim Centre for European Social Research. It provides a platform to present tools and methods for the collection, management, analysis, and visualization of data in the social sciences. Our speakers today are Alexander Wenz and Denis Cohen. Both are in the Data and Method unit here at the MZES. Denis specializes in methods of data analysis, and Alex is our specialist on survey methodology and data protection. Today, Alex and Denis will give an introduction to power analysis and present hands-on examples how to determine the necessary sample size for an experiment in advance. Before we start, a quick disclaimer. We are recording this live stream in active speaker mode. Audio from the on-site and remote participants will be recorded. And if your video is on while asking a question online, your video will be recorded as well. For those joining us online, you may ask your question by raising your hand or post them in the Zoom chat. Zoom chat. So, okay, the floor is yours.
Okay, thanks, Nadia, for introducing us, and thank you all for your interest in this topic and for coming. And also, hello to those who join online. So our talk will have three components. First, I will talk more about the basics of power analysis on a conceptual level. Most of this probably you've heard already in the Statistics 101 class. And I will introduce some analytic power calculation tools that we can use, like rather on the simple side, if you have rather simple experimental design. But these are this should serve as a foundation. And then I will turn over to Denis, who will talk about simulation-based approaches for power calculation, which are more flexible, more complex, but more flexible. So they might be more suitable to your different research designs. And finally, Denis will talk about a special case of conjoint experiments where you might want to do power calculations as well. So first of all, why should we care about this topic? So probably each of you has already had some contact with power calculation in some sense. Either you wanted to do it by yourself, or you were asked to do it by a reviewer, by some kind of external person. I mean, in the first place, the goal is to allocate sufficient resources when we collect data. So, of course, what we want to, when we do an experiment, we want to get some findings, get some insights. And we can only do that if we have an N, if we have a sample size that is not too small, because we want to detect an effect that is actually there. That's the main goal. On the other hand, too large N is also not something what we want. However, if you look, like there are some studies, some meta-analysis looking at kind of how well-powered research is, and truth is most research is actually underpowered. So you get like a kind of average of, I think, like 0.2 or 0.5 power, which is not sufficient for most cases. So the truth is rather kind of how small can you go, right, to actually get some meaningful insights. I think power analysis is also useful to kind of help thinking you through the experimental design and your statistical analysis that you plan to do at the design stage, just as a kind of check-up to kind of know that you really know what you want to measure, how you want to collect your data, and so on. So it's a rather tool for yourself. And finally, that's often a requirement by funding agencies when you write grant proposal, for example, to do such a power analysis, because they, of course, only want to fund studies that actually can get some meaningful insights, right? What are the challenges in doing such a power analysis? Big problem, or like a big challenge, is that power analysis are based on a lot of assumptions and educated guesses, and you need to get some, like you need to get some data from different sources to kind of make these good guesses. And the second point is power analysis, they do not generalize very well. So you need to calculate specific analysis for certain statistical tests. But if you want to change the statistical test, if you change your experimental design, that doesn't really translate, right? You need to redo the analysis. And I think that's kind of why these types of analysis are quite complex, because on the one hand, it's this vagueness, right? It's this educated guesses that you need to put in. But on the other hand, you need to be specific about the actual type of analysis that you want to do. Now, what kind of power analysis can we do? So in the ideal setup, I think what probably like the type of power analysis that makes most sense is this a priori power analysis. So actually before you collect your data when you design the study, the question here is, what is the minimal sample size that I need for a statistical test to detect an effect that I expect of a certain size with a given power and a given significance level. We'll talk more about these different components in a minute. But this is kind of I think the most practical application. Now, you might have encountered or you might have seen other types of power analysis that are frequently conducted. One of them is what is called the post hoc power analysis, or like a kind of observed power analysis, which is done after data collection. This is often something, for example, that reviewers ask you. You might have an experiment, you might have null findings, and then the reviewer asks you, no, but what's the power of your experiment? So the question here is, what is the observed power of a statistical test, given the effect size, the sample size, and significance level? Now, the problem with that, I don't want to go much into detail here with that. I have some pointers to some papers that kind of argued why this is not a useful analysis. Main reason being it doesn't really provide additional information if you actually calculate the power kind of given your experiment, because you would plug in your observed effect size and your p-value. But the problem is that the observed power is actually a direct function of your p-value. So non-significant p-values will always correspond to low observed power. And what you actually want to show is, right, that so you have null findings, but you want to say, I have null findings, but I have an experiment that is highly powered. And that's why kind of I still have some good insights, but that's actually what you cannot show with this type of analysis. And what some people argue is to actually conduct what is called a sensitivity power analysis after data collection. So here the focus is more, what's the minimum effect size that the test was sufficiently sensitive to detect. It's slightly different, but you could still argue kind of, yeah, where your effect size that you actually then observed lies in between. So the focus of this here will be on this a priori power analysis. Just as a kind of refresher, I said we go back to some basics from Statistics 101 when we do significance testing, right? You've all seen this this table here. Ideally, we have some hypotheses that we test. Ideally, we either have some true positives, so that means our test indicates an effect is present, and in fact, the effect is present. Or we want to have a true negative, right? So the test indicates there's no effect, and in fact, there is no such effect. Of course, like we also encounter the other cases. So one is type 1 error, like the false positive rate, or alpha, and the other, which means the test indicates the effect is present, but in fact it's not present. And this beta or type 2 error, false negatives. Okay, so what are now the key components in such a power analysis? So especially in such an a priori power analysis, one is the sample size that's to be calculated. One is the effect size. It's actually interesting when I try to look up for a kind of definition of effect size, and it's like there's not really such a clear definition of what an effect size is. But I would kind of call it a kind of standardized measure of the expected size or magnitude of an effect. So that's not necessarily effect that in the end you find, but rather something that you think is meaningful. And actually, Jacob Cohen is one of the kind of founding fathers of doing this kind of power analysis, and he called it actually the degree to which the phenomenon is present in the population, or the degree to which the null hypothesis is false, which I found quite an interesting kind of statement about that. Now, this is actually the measure that we have to kind of guesstimate, and I will talk about a couple of strategies to kind of how we can come up with such an effect size measure. Now, the third component is power. We go up to our table here. It's actually this true positive rate. It's this 1 minus beta. So that means that's the probability of detecting an effect given that the effect in reality exists, or in other words, the probability of rejecting the null hypothesis given in fact it is false. And the usual recommendation here is to set this to 0.8, although when you read the literature on kind of power analysis, you should ideally argue or kind of justify why certain of why you choose certain thresholds. But kind of point A is like, I think, what you see most often. And the final component is the significance level alpha, which is the probability of detecting an effect given that the effect does not exist. And here, I mean, you all know this, that translates to these p-values of 5%, 1%, and 0.1%. Now, briefly, so these are the four components. What's the relationship between these four components? This is a formula of power that's, I think, from the Gerber-Green book on field experiments. That's often shown for a difference in mean estimate based on two groups with same size and homogeneous variance. And I don't want to go into detail here, but the gist of it is power increases as sample size increases, power increases as the effect size increases, power increases as the standard deviation of the outcome variable decreases, and power increases as the significance level increases. So you already see here, I mean, some things are quite mechanistic. Like if we think about significance level, we can decide this measure, but then you also have other things, right? Sample size, for example, that you want to, that you might need to manipulate in your design. So I briefly went over this effect size measure and different strategies of how to come up with an estimate for effect size. And I think these are the three strategies that are often kind of recommended. First is to look into previous research and try to identify studies with a similar research design that can kind of give you an idea of how large the effect size should be also for your study. Ideally, you have multiple of such studies, and you could do some kind of meta-analysis to kind of get a robust estimate of such effect size. The problem, I think, with this approach is often that effect sizes are not so clearly reported in publications, and you often need to kind of calculate that based on the limited information that you have. But this is kind of the first way probably to go. The second way is if you have some funding for like a pilot study with like a really small sample size, this could also give you an idea of the effect size, but also on kind of how, like what's your variation in your measures. Also, what's the patterns of your missing data, which will come later to, is also kind of a factor of power, like a factor affecting power. Okay, but maybe you don't have, like maybe there are no similar studies. Maybe you don't have the chance to actually do a pilot study, and so kind of the last resort, I would say, are these Cohen's recommendations by Jacob Cohen, I think from 1988, and probably you've also seen such things. So he defined kind of in the social sciences, small like values for small, medium, or large effects. And as you can see from this table, this depends on the kind of statistical test what you want to do. So let's say, for example, we just do a simple t-test for means. He kind of claimed that a small effect size is has like a value of 0.2, medium effect size of 0.5, and a large of 0.8. So these are kind of values you frequently encounter. Again, I want to stress these are kind of the last resort measures. Like often people immediately go to these recommended values, but maybe you find some more like better estimates from actually existing research or a pilot study. Now, before going to briefly show you some of the ways to do an analytic power calculation, I just want to show you some practical consideration that you might have when calculating power. So one is the question, do I need a power analysis for every statistical test? So in theory, yes, every kind of statistical test like needs its own power calculation, but it's usually sufficient to, like, if you think about your designs, to do it for the test with the smallest expected effect size, or also kind of the most complex experiment that you think might need most power. And then power will be higher for larger effect sizes, holding sample size and significance level constant. And one thing I want to stress here is this problem of multiple testing. If you have multiple hypotheses, your probability of the type 1 error increases. So you need to kind of correct for it somehow. You might have heard of this Bonferroni correction or similar method, kind of basically adjust the alpha, the significance level. So I would argue if you could do kind of one power analysis that you clearly describe in the paper for kind of the smallest effect size and argue, well, the other effect sizes are larger, that is usually sufficient. Okay, so sample size is one of the big drivers of power, but often you might not be able to increase sample size for obvious reasons like money, basically. So what are other potential ways to increase power? And I want to briefly point you to some strategies, and they all occur at different stages. So first of all, when formulating, so again, before I say this is not meant to do like p-hacking or things. Ideally, you do this all at the very beginning, and maybe also with some kind of pre-registration. So for example, when formulating hypotheses, you could try to think, is it really that you want to test two-sided, like in two ways with two tailored statistical tests? Or maybe you have a hypothesis that goes just in one direction, and kind of really try to think what do you actually need in your study. And so one-tailed statistical tests have higher power than two-tailed statistical tests. The second thing is to consider like interaction effects require often more power than main effects. So the question is kind of also like, yeah, what's your budget? Do you actually can afford a study that also looks at interaction effects, or can you only specify kind of main effects in the onset? Okay, but maybe you have already a certain hypothesis in mind. So now that you design your experiment, what can you plan? So in general, if you plan for fewer experimental conditions, that will increase your power. Also, if you have the chance, or if that makes sense for your research design, to do like a kind of within subject experimental design or kind of repeated measures design, that also has higher power than a between subject design, because kind of it removes these between level variance. And finally, if you allocate your respondents to different conditions, balanced designs usually have higher power than unbalanced designs. So if you have same sample size in each of the groups. Okay. Finally, also some more sort of methodological approaches maybe to increase power. One is we've seen from the formula that I showed briefly that also the kind of standard error of the outcome variable has an effect on power. So kind of if you design your questions, or if you design your measures, make sure kind of you choose or you design measures with a high reliability, low measurement error that reduces the variance, because that will lead to higher power. And also missing data, of course, can highly affect power. So you might think about strategies to reduce missing values in your survey, either by, if you have, I don't know, sensitive questions, there are certain strategies where you know people are not likely to respond to, such as questions about income and like. You might consider some strategies to kind of ask it in a different way. And finally, if you don't like, you still probably will encounter missing data. You can think about imputing those missing values. Now, here, right, imputing missing values can lead to higher power, because if it is done poorly, it can also actually reduce its power. Okay, so one brief note: how should I write up such a power analysis in a paper? I would say most power analysis that you see are not described in sufficient detail, and ideally these should be reproducible and justified. So if you have some code, for example, to calculate the power analysis, maybe you can upload that together with your analysis file. Here, this is actually an example from Twitter that a psychologist, I think from Australia, posted on kind of what is the level of detail that should be contained in such a power analysis. And it could be in the appendix. So kind of what's the software you used, what type of power analysis you do, what were those different components, and also where did you, like on which basis did you estimate these? For example, on which basis did you estimate the effect size? Was it in kind of previous study or pilot study, and so on. So yeah, so I have this example in the materials later. Oh, you will have this later in the materials. Okay, now let's have a brief look at kind of analytical power calculation methods. And as I said at the beginning, these are these are for kind of rather simple situations, and you will quickly notice that kind of you will reach the boundaries of what's possible here, because they're only written for certain statistical tests, and that's where then the simulation-based approaches come in that provide more flexibility. So I think I want to show you two packages or software programs that are frequently used. One is this PWR package developed by Stéphane Champelly, a French statistician. And the other is this software called G-Power that was also actually co-developed by Edgar Ehrfelder here from the University of Mannheim, and Franz Faul from Kiel, who was a lead, or like one of the developers as well. So let's first look at this PWR package. You basically have functions for the different statistical tests that you want to do. I think actually this is already the almost complete list of tests that are available. I think ANOVA is another statistical test that's covered. But you see kind of this is, they cover a lot like kind of proportion tests, t-tests, and so on, and the like. And what you can also do is do a power curve. So basically to plot power as a function of sample size with just with a plot command. Actually, it uses, if ggplot is loaded, it also relies on ggplot, and you can kind of make some fancy graphs, or it will use base bar. So let's briefly walk you through these commands. I'm a survey methodologist, so I have a kind of survey methodological example for you. So let's assume we're conducting a student satisfaction survey at the University of Mannheim, and we want to know if a Café Soleil voucher of €5 as an incentive increases the survey response rate. And let's say this incentive is announced for half of the sample in the invitation email, and it is not announced for the other half. And for each student, we observe whether they participated in the survey or not. So like a simple binary outcome, 1 or 0. And we want to test for this, for this difference in proportion using a 2-sample t-test. My question is, what's the minimal sample size to detect an effect in either direction? I don't have any hypothesis in which direction it should go. With a power of 80% and a significance level of 5%. And the first question I will have is, what's my effect size? And I mentioned we have the different strategies. So maybe I have, maybe there hasn't been a study that actually looked at that in a student context. But maybe I have some money to do a brief pilot study, or I've done a pilot study in some other university. And so then this PWR package also has some functions to actually calculate this effect size, so the standardized measure. So let's say that's this es.h function. So let's say I have in one group, in the group where people will announce the incentive in the email, like 30% participate of the students, and in the other group where no such incentive is announced, only 20% participate. And so I plug in those two values, and here in the comment, I showed you kind of the calculation, what's done to compute this effect size. And we see we get this effect size of kind of 0.23. According to Cohen's recommendations, this would be a small effect. So let's go to, and that's also implemented here is for the different statistical tests that you can indicate, and with a function Cohen.es, and then indicate whether you're interested in a small, a medium, or a large effect. You would also get those values, so you don't even have to look them up. So, okay, so now I have these two sources. Let's say I go with 0.2 with an effect size of 0.2. I choose the appropriate function to do this kind of test for two proportions with an equal size. So one half was assigned to one condition and the other half to the other. I plug in here this effect size of 0.2. I plug in the significance level of 0.05 and the power of 0.08. And basically with all these functions, whatever component you want to calculate, you leave empty, or you write n equal null. I also specified this is like a kind of two-sided t-test. And then the package gives me kind of this, like all these numbers, and I'm interested in this one here. So I would need 393 respondents, and that's in that's in both groups. So basically this number times 2 to get like the overall like kind of 700 something response to do this type of study, to be able to detect my expected effect size. I mentioned this PWR package also kind of is able to plot power as a function of sample size, and I simply wrap my function that I showed you just now with a plot command, and it returns you this value here, so you can see kind of what's which power can you reach with kind of sample size here. And again, this is kind of for each group, the sample size that you need. Okay, just briefly, before I turn over to Dennis, this other software, that's G-Power, that's free software available for Windows and Mac. And this can be downloaded, I think, from the University of Düsseldorf. And this is a very point-and-click way of calculating power, although you can, I think, also use some syntax and also actually download the kind of syntax that you use for kind of replication purposes, or kind of to put that in the paper. You basically select the statistical test, what kind of power analysis what you want to do, you input your parameters, and then click calculate. And as you see, I mean, this is the interface. Unfortunately, I can't make this bigger here, but here you see basically you select the kind of tests. What you want to examine, whether that's an a priori or some other type of power analysis, and calculate those values. And it should give like estimates that are quite similar in a similar range. I mean, it uses different types of calculations in these, like in the R package versus the G-Power, but should be in the same ballpark. Okay, in the material I also have some more like some pointers to some publications that I think are quite interesting also to read. Yeah, and I mean, as I showed here now, you're quite limited in the kind of statistical tests, of course, that you can look at. So that's why, or that's where the simulation-based approach.
As Alex just said, there are certain limitations to doing analytical power calculations, and the simulation approach essentially unlocks all the potentials that the analytical approach doesn't grant you. So once you think you're dealing with slightly more intricate analytical problems where you no longer want to apply standard difference in means or difference in proportion tests or compare correlations, variances, or something across binary groups, but you're interested in applying somewhat more intricate estimators to perhaps nest the data, or want to add a little twist to your analysis, whichever form or shape that may take. The simulation approach allows you to accommodate that at the expense of having to set up an idiosyncratic pipeline. And I'm going to demonstrate now in very simple and rudimentary terms how this can look like. The approach in general, regardless of how complex your specific analytical problem down the road might get, looks as follows. We usually start with a loop or some other sort of replication exercise where we have multiple iterations that repeat one and the same procedure. The first step always involves simulating realistic right-hand side data. By that, I mean everything that goes to the right of a parametric regression model. And this is, of course, subject to design choices. So if you have some sort of clustering or hierarchical nesting in your data, you would automatically incorporate this in the simulation of this type or this set of data. What you then do is you mimic the data generating process or the generative model for the left-hand side data, so the outcome. And you do so by setting true parameter values, and then use those true parameters and the x or right-hand side variable that you've already simulated in the first step to mimic and simulate this data generating process for the outcome. This then gives you simulated y data, simulated x data, which you can use in the third step to apply the estimator of your choice to get the estimate or estimates of your target estimates. And this can, of course, be also a difference in means, but it can also be something rather funky, like a quantity of interest that is some sort of ratio between two predicted probabilities, so a probability ratio, or whatever your research interest desires. You will then likely have a specific null hypothesis in mind or alternative hypothesis in mind regarding this specific quantity of interest. And that, of course, allows you to recover a p-value of this specific estimate at the current iteration. You can then, given your predefined alpha value, determine if your p-value falls below this alpha value and store the result as significant if that is the case, or as insignificant as that if that's not the case. So you essentially just record a binary evaluation for the current simulation of whether the p-value for the estimate regarding your quantity of interest falls below your alpha value, which we usually set to 0.05. And then we repeat these 5 steps over and over for a large number of simulations, where by large, I would usually recommend at least 1,000, but in the interest of keeping our computing time short and crisp, we will work with lower numbers here today. So in the end, you then have a vector of length s that records the binary information for each iteration of the simulation exercise on whether you recovered a significant effect or not. And the simulation-based power is then simply the proportion of statistically significant estimates out of those S, so let's say 1,000 iterations. The benefits of doing this are flexibility. The first step, so the step where you simulate the right-hand side data, allows you to incorporate design choices and data structures at any level of complexity. So this can include forms of random assignment and randomized control trials. So things such as simple, complete, block, or clustered random assignment. You can choose the structure of your treatment. So whether you have a simple binary treatment, a multi-categorical treatment, or continuous treatments, and you can incorporate multiple levels of clustering, grouping, or nesting in your data as well. Step 2, so the step where you set the true parameter values and simulate your outcome variables, allows you to incorporate details of the data generating process at any level of complexity. So here we can stipulate models for binary, multi-categorical, ordered, continuous or bounded continuous, or count outcomes, and also include effect heterogeneity as part of the simulation exercise. And in step 3, where we then apply the estimator of our choosing to retrieve the estimate of our quantity of interest, really allows us to choose any type of estimator or statistical model that we may want to apply to estimate the quantity of interest that we are interested in testing. Okay. So we'll start with a very simple example, namely a very basic randomized control trial. So we have a binary treatment, can take on the values of 0 or 1, where 0 marks the control group, 1 and 1 marks the treatment group. And this will be assigned using complete random assignment with a probability parameter of 0.5. So equal probability of being in treatment or in control. And our outcome variable y will be continuous. So let's say we're studying an outcome y that has been recorded in pre-existing data, let's say a survey. And we know from this existing data that also consists of a representative sample of the same population that we seek to study, that the mean of this variable y is 1, and the standard deviation is 0.75. So therefore, given that we seek to take a random sample from the same target population, we should expect that in our control group, the mean will also be 1 and the standard deviation will be 0.75. Now, we expect, for some reason, one of the manifold approaches that Alex has sketched in his part of the presentation, that receipt of the treatment will on average increase y by amongst the unit in the treatment group by 0.2 points, such that the average treatment effect is 0.2. So we can implement this by parameterizing the scenario through a simple linear model. So here we have our y, which is a function of an intercept alpha, the treatment effect tau, and the binary treatment d, with an error term, and this error term is a zero mean normally distributed random variable, where the variance is this value of sigma 0 that we recovered for the control group, so based on pre-existing data. So we can plug in those values here, the mean in the control group that we know from pre-existing data, the variance or standard deviation in the control group that we know from pre-existing data, and this value that we think is most plausible as a guess for the treatment effect. And we can set up a corresponding function. So here we then have a custom power function. We call it power underscore sim. And it has a series of of inputs or arguments. There is n, the sample size. Then we have the parameterization of the linear model. So we have the intercept mu0. We have the slope or treatment effect tau. And we have the variance of the model, which is by default set to 1, but we can plug in any value that we like later on. We then have the probability parameter that governs the random assignment of the binary treatment. We have our alpha value here, which by default is set to 0.05. We specify the default number of simulations, which is 1,000 here, and we set some seed for replicability. Now, the function works as this. First thing we do, just to ensure that everything that we do remains replicable, is we set a seed, where the seed is just the number that is supplied up here as an argument to the function. And then something happens inside a replicate command. That means we want to replicate a certain operation n-sim times, where n-sim, of course, is the number of simulation. And we replicate everything that's in between the curly braces, let's say 1,000 times. So what happens inside these curly braces? The first thing we do is we mimic the data generating process. And here we essentially say, well, we take the assumptions of the linear model seriously. In the control group, we believe, which is essentially a null model, where the intercept is mu0 and where the variance is sigma 0 to the square. We essentially say this is just a draw from a normal distribution, or a sequence of draws from a normal distribution with n observations, with this mean and this variance. So essentially just use random number generation to simulate the outcome in the control group. And then, per the assumption of the model, nothing really changes from treatment to control group, except one thing: we add the treatment effect, in our case, of 0.2. So we simulate y, so the potential outcomes in the treatment group, by simply adding the treatment effect onto the potential outcomes under the control condition. In the next step, we then simply generate a vector of length n of the binary treatment. So it can be either 0 or 1, and it should be fairly balanced in the end, because we're using a complete random assignment with a probability parameter of 0.5. And then we define the observed outcomes y by revealing the potential outcomes that correspond to the treatment condition. So if d, the treatment indicators, equal to 1, indicating that an observation is in the treatment group, we assign the potential outcomes under the treatment condition, the y1s. And if d is equal to 0, assigning somebody to the control group, we reveal the potential outcome under the control condition, which is this y0 here. Now, in the next step, we simply have to apply our estimator, which here is a simple OLS. So we regress y on d. And what we then want for this model is the p-value for the slope coefficient. So the p-value for the treatment effect. And this information is hidden in the summary of this OLS object in the coefficient matrix, and namely in the row that records the effect for the variable d, and in the column that records the p-value, which is given by this expression here. So the probability that the t that we record in the t statistic is greater than some value. And here we just want to make sure that this p-value is smaller than alpha. So what we get as a result of this evaluation here is simply a true or a false. This will be true if the p-value for our treatment effect is smaller than 0.05, and it will be false if it is greater or equal to 0.05. And this will then be returned as a result of this function. And we do this for every iteration of the simulation exercise. So what we get here in this object num_sig is then just a length 1000 vector of trues and false. And what the function overall returns in the end is just the mean of trues as opposed to false. So if in 800 out of 1,000 iterations we get a true, the proportion will be 0.8, and this would be our simulation-based power estimate. So we can check what this looks like by applying this function. We can set an n of 500. We plug in the values that characterize or parameterize our models. So a value of 1 for mu 0, a value of 0.2 for the treatment effect tau, and a variance of 0.75 or standard deviation of 0.75, and we use the default arguments for everything else. And what our function would then return, and it takes a little moment to compute, is that with a sample size of 500 and an assumption that the treatment effect would be 0.2, we'd have a simulation-based power estimate of roughly 0.85.
Can I ask a question?
Of course, man.
So, in your simulation, every loop, you're recreating your data?
Yes.
Intuitively, I would say you want to create the potential outcomes once, and then every loop reshuffle the assignments.
No, you actually have to, so as far as I'm aware, you have to simulate the data at every turn.
Okay. So I'm just thinking like what is randomization inputs? Like you're reshuffling your assignments, but you assume there's a true schedule of the potential outcomes.
Yes, but you're also re-simulating your right-hand side data. So, I mean, by and large, in this simple case, it shouldn't make a difference, yeah, right? Because every random simulation of your y0s and y1s should, in expectation, converge to the same distribution. But as far as I'm aware, you do both the right-hand and the left-hand side simulation anew at each iteration.
So just to clarify, in this, what you're doing here is you fix the effect size, right? Like the effect size in all simulated data sets is 0.2, right?
Yes, the parameterization is constant across all simulations. Yes.
And the sample size is the same, and now you power for a given n. Sorry.
But you fix the effect size for every single observation, right? So it's not that the average effect. I mean, it's like I said, the average effect is 0.2, but it is also literally 0.2.
It is, yes.
Yeah.
So this is deterministic. Yes. Yes, so we have no heterogeneity in treatment effects, but we could incorporate this as part of the simulation if we wanted to. Okay, so one other thing we can do, of course, is repeat this calculation or simulation exercise for a sequence of sample sizes, hypothetical sample sizes. So this is the idea underlying a power curve. We have a sequence of n values, so sample sizes, and we want to calculate power anew for each of these values. And this is exactly what we do here. So we define a sequence that runs from 100 to 1000 in steps of 100s. And at each of these values, we calculate our simulation-based power. And this may take a little moment to compute. So what we get then is, this is not just a tabular format, but you could as well imagine this in plot with n on the x-axis and power on the y-axis. We see how power increases as we increase sample size, and we see that while going from 100 to 1000, power increases from roughly 0.25 to nearly 1. Okay, so this would be then just a simple implementation of a simulation-based power analysis for a very simple RCT under the assumption of homogeneous variances in the treatment and control group. Now we're going to make this example slightly more intricate by relaxing the assumption of constant variances. So suppose what we just did is based on, or we do a pilot study, and as part of this pilot study, we realized that our assumptions were a bit off or overly simplistic, because we realized upon inspecting the results from our pilot study that receipt of the treatment not only results in a positive shift of 0.2 in y, but also increases the variance in y. So receipt of the treatment not only shifts opinions or outcomes, it also polarizes them more. So therefore, we want to incorporate this feature of having non-constant variances across treatment and control groups into our power simulation. And we also want to change our estimation a little bit by now rerunning our final models with heteroscedasticity robust standard errors. So the idea now is that we parameterize the data generating process in terms of group specific means and variances, where we now have a mean of 1 and a standard deviation of 0.75 in the control group as before, whereas in the treatment group, we now have a mean of 1.2, reflecting the same effect of 0.2 as before, but we now have a larger standard deviation of 1.25. And as before, we want to estimate the eventual treatment effect using OLS. So here we have a similar function as before, just that we now have the parameters that characterize the data generating process in terms of group-specific means and standard deviations. And what we do as part of the simulation exercise is we again generate the potential outcomes, given the mu1s, mu0s, and corresponding standard deviations. We reveal potential outcomes again as a function of this completely randomly assigned treatment. And we change the inference method a little bit in the sense that we now use an OLS with heteroscedasticity robust standard errors. And here, similarly as before, the p-value of interest is hidden in a coefficient table, which is named slightly differently as in a standard LM model. So in this fixed FEOLS command, the corresponding table could be found by simply using the $ operator, coef table, and then selecting the correct row and columns. So we do this. I'm adjusting the sequence here a little bit. We now look at sample sizes from 250 up to 2000 in steps of 250. And we want to see what this updated power calculation looks like. And I can already say we should expect that we need larger sample sizes to reach the same amount of power, given that we now have more variability, at least in part of our data. This takes a little while to compute. And what we can see here is that if you remember with 500 observations, so a sample size of 500, we had a power of roughly 0.85 before. We're now considerably lower, but we can, of course, once again see that with increasing sample size, power increases, and we hit a threshold of 0.8 with a little less than 1,000 observations in our sample, and converge towards 1 with 2,000 observations or more. So this is just a little illustration of how simulation allows us to continuously increase the complexity of what we think the data structure and data generating process looks like, and allows us to incorporate these features and apply any estimator that we want. So the main takeaways here are then that power simulation is a very powerful tool whose main strength is flexibility, but also acknowledges that these benefits come at the expense of some effort of setting up the simulation pipeline, which of course critically depends on you getting the data generating process right in terms of your simulation pipeline. And possibly it comes at the expense of longish computation times, but that's a work your computer can do for you while you have a coffee or attend the social science data lab, so that's not too bad. Okay, any questions up until here? Yes, Romeo, please.
What size, like, as you said, like, it depends on how many, like, how large a simulation is. What's the standard, like, thing that you would do for power analysis, like?
Oh, it really depends. I mean, you saw how long this computed with, I think, just 10 different sample sizes and, I don't know, 200 or 500 simulations each, with a lot more intricate pipelines for setting up the data generating process, larger number of simulations which you should choose. This could be in the hours or days.
No, but like, is there a standard of how large a simulation you would run, actually? Like, how many repeated?
Oh, so I would say 1,000 as a minimum, okay, but that's a gut feeling. I mean, my standard teaching example would be simulate a normal, like take random draws from a standard normal distribution and be the judge when the histogram really approximates the underlying probability distribution. And usually we would say 100,000 would be ideal, but I wouldn't necessarily recommend that. Yes,
I don't want to beat a dead horse, but I mean, couldn't you save time if you just simulated the data once and simply looped through the assignment, simply looped through the reveal step?
The treatment assignment.
Yeah, or which of the which y1 or y0 is revealed, and this is what's looped through, but the data is just, it just sits there.
Yeah, I'd have to think about this also, whether that works. Is that a two-finger comment on it? Yes, go ahead.
When you, I would say when you only generate the data once, then you assume that you have your sample. Dennis made the assumption about the standard deviation of y in the population.
Yeah.
Your research design contains the random sampling process. The standard deviation in your sample, untreated, will not be exactly the population standard deviation. So there's variation in there. If you already have your sample and measured y pre-treatment, then you can probably do that. And then the remaining variability is just a treatment assignment. So that's the only thing that you randomize. But if you didn't do the sampling yet, you only have a guess about how y is distributed. And this is part of the research design that I would say you need to account for.
Sounds great.
Yeah, it's very, very simple question, but I still didn't get how you came up with the effect size 0.2 there in your example.
Yes.
You will always need to like base it on previous study, like pilot study, or
So I mean, Alex discussed some options on how we could do this, right? So one is you may need to help me here, but one is you run a pilot study. Then there's Cohen's values, which are based on standardized effect sizes, and the third one was
Previous research.
previous research.
and in your example,
It was just a value I made up, but it could be based on either.
okay.
Yes. Marian, was that a question?
I just wanted to say, like, substantive interest would probably also go. Like, if you want to really find something of a difference, like how much percentage points of an increase of like a party vote share would be of interest, I guess. You would probably not choose like 0.02 percentage points.
Anything else? In that case, I'll move on to something that is pretty much still in flux in the world of political science and beyond, and that is power analysis for everyone's favorite experimental design, the forced choice conjoint experiment. And I'll start with two disclaimers here. The first being that power analysis for conjoint experiments is, as of today, still a moving target. So as far as I'm aware, there have been 4 widely received, discussed, and already cited sources on power analysis in conjoint experiments since 2002. 2 of these are working papers and 2 of these are online tutorials. And these are Brett Gall's. I think this was the first one, published on October 6th, 2020. A blog post or online tutorial, simulation-based power calculations for conjoint experiments. Just 6 weeks later, Alberto Stefanelli and Martin Lukács released a working paper that to this day, as far as I'm aware, hasn't been published yet. Just a month later, Julian Schützler and Markus Freitag followed up with a paper, Power Analysis for Conjoint Experiments, where the main difference between the 2 was that the first one was simulation-based, the second provided an analytical solution. And then in 2022, Robert Hubenek followed up with another online tutorial or blog post that simply documented a power analysis he had done for one of his working papers, so a substantive applied analysis that, however, didn't cover the classical forced choice binary conjoint, but a rating-based conjoint design. So all of these are super interesting to read, so I recommend you look at the originals. But one thing that is also important to note is that all of these focus on inference with respect to the average marginal component effect, so the AMCE as the central quantity of interest, or the average component interaction effect. Which brings me to the next disclaimer, namely that applied conjoint analysis, and in particular, the quantities of interest that we ought to use in conjoint analysis, is in and of itself a moving target at the moment. So I'm just listing 6 publications here, recent publications on conjoint analysis. And what you will realize is that 5 out of these 6 contributions focus on estimates or quantities of interest that one can tackle as a result of a conjoint experiment. And 4 out of 6 challenge the use, or at least the conventional use, of the AMCE, so the average marginal component effect. So it seems then consequently that there's increasing demand for quantities other than the AMCE, and prospectively also demand for approaches to power analysis for quantities of interest other than the average marginal component effect. So with these 2 disclaimers in mind, let's briefly recap what a conjoint experiment is and what it looks like, and also let's clarify some notational aspects here so we all know what we're looking at when we see the formal notation. So binary forced join settings have 2 profiles side by side, and you're forced to choose which one of the 2 you prefer. Each profile is a combination of C components, where each component is displays a random draw out of several levels. So there need to be at least 2 levels per component. For example, if you have 2 political candidates side by side, it could be their gender, where we would mostly use a binary conceptualization of gender, and therefore have 2 levels, but it could also be something like age within 5 different age brackets in which the number of levels for this attribute would be 5. Today, we will denote the realization of the component xc with this given level using lowercase x and then c and l as subscripts. So without constraints on impossible component combinations, all the number of levels or unique profiles is given by this product term right here. So an example would be a simple 3x2 design. We have 2 components, the first of which is instructor and the second of which is topic, and the outcome is a student's choice for a hypothetical elective. So you have different courses taught by different instructors, total of 2 topics, total of 3 instructors, and you want to know if you have combinations of topic and instructor and 2 of those side by side, which ones are students more likely to choose. So given that we have 3 instructors in X1, there's 3 levels here. Given that there's 2 topics in X2, we have 2 levels there. So all in all, this is a 3x2 design with 6 unique combinations. The choice task is then this. Each respondent, so each hypothetical student in this thought experiment, evaluates up to J unique sets of K profiles. And given that we're looking at binary forced choices, we can already say K is always going to be 2. So in other words, each respondent gets a set of binary profile comparisons. And as I already said, 2 profiles side by side, the 2 profiles must differ, and there needs to be a forced binary choice, meaning if you choose one, you cannot choose the other, and you're not allowed to choose neither. This is what this may look like for one respondent who is prompted with 3 evaluation tasks. You see 6 rows. Each of these are pairs where you have one task with 2 profiles that are displayed side by side. So for respondent 1 and task 1, you compare, for example, a hypothetical elective where instructor 1 teaches on topic 1, compared to a hypothetical elective where instructor 2 teaches on topic 2. And in this case, this hypothetical respondent 1 would opt for the second option, so topic 2 taught by instructor 2. And then you present them with yet another pair and yet another pair. And therefore, we have 3 evaluation tasks for one and the same respondent displayed across those 6 rows. In terms of estimands and estimators, actually not going to talk much about estimators here. It's usually just OLS. So let's talk about estimands only. There's usually the marginal mean, a quantity that has been popularized by Lieber et al.'s paper in 2020, which describes the level of favorability towards profile that have a particular feature level, ignoring all other features. So here you'd want to know which profile does somebody choose, given that we set x1, so in our case that was instructors, to a specific level, averaging over all the values for x2 within the same profile, and averaging over all possible combinations of both features in the rival profile. Everyone's favorite quantity of interest is, of course, the average marginal component effect, or AMCE, which represents the marginal effect of a component, or in this case, the first difference of component level versus a hypothetical reference level. And this is then averaged over the joint distribution of all the remaining features. So what we essentially have is the marginal mean, where we set one of the features to a specific level, and then we have the marginal mean where we set the same feature to a different reference level. And the difference between those two gives us the AMCE. We can, of course, as we always can, condition this on something else. So either the value of the level of another feature, which would give us causal interaction, or on a respondent trait, which would give us some idea of non-causal effect heterogeneity, conditioning on respondent characteristics. And what this conditional AMCE then is essentially just a conditional marginal effect, where we are now conditioning the same quantity as before on a specific level of a respective other feature. This is closely related to the average causal interaction effect, or ACIE, which follows pretty much the same intuition, but uses a difference in difference logic, in that we're also differencing out the respective other dimension. So here, for example, we have the difference same as before. So we have a hypothetical shift in the level of the first feature while setting the second feature to a specific value. And then we do the same shift here, this time, however, fixing feature 2 on a specific level. And then the difference within those two differences, so to speak, the difference in two conditional AMCEs would give us the average causal interaction effect. And the last quantity of interest that I'm going to talk about here are cell means, which are just the mean outcome for each particular combination of feature levels, and they give the average popularity of a fully specified profile. So in this case, this would be what is the average probability of a course taught by instructor 1 on topic 1, and this would allow us to test hypotheses like, I don't know, topic 1 taught by instructor 2 is at least twice as popular as topic 1 taught by instructor 3, or something like that. Okay. Last thing about the basics here is a note on uncertainty estimation. In this very popular Heinmüller et al. 2014 paper, the authors proposed an adjustment for within respondent clustering of tasks and choices, using either clustered robust standard errors at the respondent level or log bootstrapping at the respondent level. Now, in their working paper, Schutzler and Freitag, referring to a recent paper by Abadi, refute the necessity of clustering and show that doing so is in fact inconsequential for uncertainty estimation of AMCE standard errors or confidence intervals. This is also confirmed by a simulation study that's in Kubinek's online tutorial, where he shows that using clustered standard errors really makes no difference unless the sample size is very, very low. And the reason I mention that is that there's a certain benefit to foregoing clustering that Schutzler and Freitag use and leverage. And this is that one can simply use unadjusted estimates of the variance-covariance matrix of OLS coefficients for simple closed form or analytical power calculations. And this is exactly what we are going to do next, where I'm just going to sketch the analytical approach of Schüssler and Freitag to closed-form power analysis for AMCEs in conjoints. So the preliminaries here are fairly straightforward. We already said that we have n respondents who are prompted with j tasks comparing k profiles. And the product of these three numbers is what Schüssler and Freitag refer to as the effective number of observations. So respondents times tasks times size of the profile set give us the effective number of observations. And of course, all of these n, j, and k affect power. What does not affect power is the number of features that we have in a conjoint. Because since all of these things, so one feature is through randomization independent of another, having many of these shouldn't affect the power of any one given AMCE. What will, however, affect the size of the AMCE is the number of levels for our focal feature. Because in expectation, respondents only get to evaluate a specific number of profiles involving a given feature level. So if we have some number of effective observations, and there's only 2 levels for a given feature whose AMCE we want to compute, we will get a lot more of these profiles involving this feature level as compared to, let's say, a feature that has 5 levels, where this number is going to be a lot lower. So the idea that they leverage then is that we can add a little twist on the OLS estimation of average marginal component effects. If we were, for example, interested in the AMCE of which instructor is teaching a class, we'd usually just run a linear model of this form, where alpha captures the marginal mean of a class taught by instructor 1, and then we'd have the respective differences in popularity of the hypothetical elective for instructor 1 if we added beta 1, or for instructor 3 if we added beta 2. Now, if we consider this trichotomous feature x1, and suppose that our quantity of interest is just the AMCE of having instructor 1 as opposed to, sorry, instructor 2 as opposed to instructor 1, we know the following. Each of these profiles involving each of the 3 levels would on average appear the number of effective observations divided by 3 times. This also means that in estimating the AMCE, or the pairwise first difference of having instructor 2 in the profile as opposed to having instructor 1 in the profile, would effectively ignore all observations that involve the 3rd level, so instructor 3. Which would then mean that the estimation task is equivalent to a simple binary regression, where we only have a binary indicator of whether we have instructor 2 or 1, dropping the subset of profiles, so roughly 1/3 of the observations, where x1 is instructor 3. So essentially, it's just a binary estimation task based on 2/3 of the data. And due to simple randomization of feature levels, the probability of having instructor 2 or not having instructor 2 should be roughly 0.5. So in the end, what we're doing here for this very simple task of focusing on just one AMC is we're redefining the problem pretty much like a simple binary RCT. This allows us then to come up with fairly straightforward derivations of the variance of the resulting estimate. So the idea here is that we have this formal expression here for the variance. And since y is binary, we can re-express the variance simply in terms of variances of proportions, which are given by p times 1 minus p. And p is then just the average, or the marginal mean, which would be, give me 1 second. So tau 0 plus tau 1, intercept plus slope for all profiles involving instructor 2, and it would simply be tau 0 for all profiles involving only the reference, so instructor 1. Which then means that the variant only depends on 4 inputs, the levels, the number of effective observations, as well as the estimates of this simplified estimation tasks. So just an intercept and a slope. And this then allows us to plug in those values to the same power formula that we saw before. And we could make the conservative assumption then simply plugging in the value that maximizes the variance, which is a value of 0.5 for tau 0. And in the end, this would then allow us to come up with a fairly, I mean, there's still some math going on here, but a fairly simple derivation of an analytical estimate for, let's say, the required number of effective observations given an alpha value of 0.05, a beta value of 0.2, which would mean a power of 0.8. And given that we have 3 levels here, we'd come up with a value of roughly, well, it's given by this expression here, so it means it all depends on the effect size, of course. But we're essentially down to a problem where we can choose the required number of effective observations as a function of our a priori expectations about the AMCE tau 1, because this is the only unknown that's left in this expression here. So by simply plugging in a value for tau 1, we come up with the required number of effective observations. And given that we know that we have 3 choice tests per respondents, 3 levels for this feature, and binary comparisons, so sets of 2 profiles in each task, we know we simply have to divide this number by 18 to get to the required sample size, so the required number of respondents. Schüssler and Freitag provide an R package that does all this work for us. It's called CJ Power. It's on Markus Freitag's GitHub, where you can retrieve it from. And it's fairly simple here. So we can plug in a value for the AMCE of 0.05, define the alpha, define the power, the number of levels. And as in the PWR package, we set the component to null for which we want to get the required value, which in our case is the sample size L. Oops, sorry. And as we can see right here, with a feature that has 3 levels, setting the requirements for alpha to 0.05, power to 0.8, and the expected a priori expectations about the AMCE to 0.05, we need an effective sample size of roughly 4,700. And dividing this number by 18 would then give us the required number of respondents. We can, of course, do this a bit more systematically or turn it the other way around. So let's say we have 200 respondents, we have 3 levels, 3 tasks per respondent, and 2 choices per task. What would the power be that we get out of this, given that we think that the AMCE is 0.05? And we can see with just 200 respondents, we get a power of roughly 0.69. Another thing we can do, as before, plug in a number of effective sample sizes and visualize the whole thing using a power curve. So here we do this, takes a moment to compute. So now we have the number of effective observations, which once again, for the running example, we'd have to divide by 18 to get to the number of required respondents. And we can see how the power curve increases as a function of the number of effective observations, where we'll probably hit a threshold of 0.8 at around 8,000, maybe 4,800 effective observations. Okay. There's also a Shiny app, which is currently not available, it seems, but it's out there, so you can plug and chug in some values. I would generally recommend this. As I said, it's not published yet, but it seems fairly straightforward. The math is simple yet elegant. But there are some limitations, which are few but notable. The first is we're only looking at binary forced choice designs here. So there's no rating-based conjoints. There's no multinomial forced choices. So it's slightly limited in that regard. And of course, we're only looking at AMCEs or conditional AMCEs here. That means we have no marginal means, no cell means, and no funky functions thereof that would allow us to test slightly more intricate hypotheses. So the key takeaways from this is that we can treat power analysis for any single pairwise AMCE as a difference in means or difference in proportions exercise, estimated via linear regression on a subset of the data. And details aside, power analysis for any singular AMCE is therefore widely analogous to power analysis for the ATE using a difference in means estimator. The problem, of course, is in conjoint analysis, we're usually not interested in just any singular AMCE, or perhaps a CIE or conditional AMCE, but we usually are interested in pretty much all pairwise comparisons, and we want to be able to conduct hypothesis tests and sufficiently powered hypothesis tests for all. So the idea here would then be that we need to conduct power analyses for the AMCE, conditional AMCE, or a CIE for all features and all pairwise differences of feature levels within each feature. And this would mean in the case of conditional effects, of course, then also possibly all pairwise feature level interactions. And this would get us a distribution of required sample sizes for all the different estimates that one could possibly derive from a singular large conjoint experiment. And then the question is pretty much what you want to do. Do you want to choose the maximum required sample size just to be safe and have some insurance that even your most fragile, so to speak, estimate will be sufficiently powered? Or will you probably opt for a more pragmatic choice and subject this choice to your financial budget constraints? It's a call you will have to make in the end, but if you're really interested in a higher level interaction, it may take a very large number of respondents to ensure that this higher order causal interaction is truly well powered. In the interest of time, I think I'd conclude here. I still have a number of slides on simulation-based power analysis, but this is currently still pretty much work in progress, with 2 papers also taking contrasting approaches on how this is best performed. Again, the benefits of simulation is its flexibility and its ability to down the road also accommodate quantities of interest other than just the AMCE. The very, very different problem or very, very difficult property of forced choice binary conjoint experiments is that the data generating process is very funky, because choosing one profile over the other is a binary choice, so a Bernoulli trial, if you will, where one thing comes out with a 1 and the other with a 0. But it doesn't only depend on the properties of the profile itself, but also on a randomized rival profile. And therefore, you essentially have a binary choice for or against a given profile, which don't only depend on the properties of the profile itself, but also on some randomized and therefore hard to predict or hard to grasp features of the respective other profile. And there's pretty much 2 ideas in the existing literature, 1 working paper, 1 online tutorial on how one could handle this. One thing is to think of differences in the features on the right-hand and left-hand SAM profiles. So let's say you have instructor 1 in the one and instructor 2 in the other, and you have some a priori expectations about what the AMCE is, then you know that the AMCE or half the AMCE needs to be added to the popularity of one profile or subtracted from the other to come up with this AMCE in the end. So thinking about this in terms of differences in profiles is one way. The other is to start with unconditional choice probabilities and simulate binary choices from that. So you have an unconditional choice probability of profile 1, profile 2, and you relate the 2 to one another, eliminate the possibilities where people would, in independent Bernoulli trials, choose both or neither. And from the balance of those where they would choose one over the other, as opposed to the other over the one, you can construct a probability parameter for this Bernoulli trial. This will be in the materials that we are going to upload, so feel free to look at this, but I think for the last 10 minutes or so, we will reserve some time for your questions.
It's super interesting. I think I've learned not to simulate conjoints, but I mean, so I really like this analytical approach. I don't understand though why you can ignore clustering. I understand like it's maybe empirically true. I just don't get it at an intuitive sense. Like, given that if you pick one here, the other one has to be zero. Why would you?
Yes, so I mean, there's two levels of clustering, if you will, right? There's this deterministic correlation within each choice task. So if you choose profile 1, you cannot choose profile 2. The other, and this is the one that has been recommended in the existing literature, is the clustering by respondents. So you have multiple tasks per respondent, right? So let's say a series of 3 tasks where you have to make a binary choice. And here, the paper that Schüssler and Freitag referred to, the Abadi et al. Paper, makes the point that adjusting for clustering only makes sense if treatment assignments happens at the level of the cluster. And this is not the case here because we're randomizing each choice task. So each choice task within each respondent is being randomized. You don't get a receipt of a randomized treatment at the level of the respondent. And I think this is the point that they make here. I mean, the good news is clustering won't do any harm. The only reason I believe they want to ignore it here and make the strong point that they don't need it is because they just want to use the raw covariance matrix from the OLS estimation, because this simplifies the analytical derivations of the power calculations.
I kind of have more back to the statistics 101 question. Just to grasp it, if I have now like a power of 0.8, meaning I have a probability of 80% that I find the effect of the size I think that is interesting, or at least that I think that is interesting. What is the possible outcomes of this? Now I have my sample, I have my power analysis. I test, I don't know, 500 people are enough. I draw my sample of 500 people. I run my analysis. Now, what can I find? What if I use my power analysis with 0.4 and now I find an effect of 0.3, but it's still significant? Is that possible? Does that fall in the other 20%? Or where is that?
I mean, maybe the answer to this is the thinking that also like effect sizes and power, that's also kind of a random variable, or you should also think of this as a kind of population parameter. So kind of when you think, so like in your example, you're like the 80% power. So that means in 80%, in 80 of 100 trials, you would detect the true effect given that it exists, but in 20, it does not. So your kind of achieved power might still be lower in the end, depending on the actual kind of effect size you actually get. But kind of this thinking of this a priori power analysis is really kind of what's your expected effect size in the population, or kind of in the ideal world, and then in your actual case it might be lower, right? Does that answer?
Yeah, it answers. That's kind of like the power of what I actually draw also depends on the real power given there's a real value or real effect.
So kind of your like power that you actually get is kind of one realization basically of this kind of random variable then.
So the power that I get from the sample I draw does not have to be the power that I had predicted in my power analysis, because that was based on a world where the effect is at least as big as I want it to be.
I think that's also how this a priori and this post hoc differs, where in the post hoc you actually calculate it based on your values that you have. But I think the kind of value of doing this a priori is right, like independent of what you actually get, like what's the minimal size you need, right?
still trying to understand the last part with. So you said the number of attributes I add to the conjoint does not directly affect the power, right?
For the ANC.
For the ANC, right? But of course, once you talk about interactions, changes everything, right? But wasn't in the effective in there were just the levels for the one I'm interested in?
Yes, for the levels of the attribute, or for the levels of the feature where you're interested in a specific.
But if I have like 100 other attributes, I still don't care about.
Yeah, I mean, this would probably, I mean, in terms of respondents ability.
Yeah, no, I understand that.
Yeah, but I mean, mathematically speaking, it doesn't make a difference between at each, each randomized profile still, if you have a binary or two levels for one feature, you'd still have those in every profile pretty much. So yeah.
And then you said as a follow-up, so but then if you have many of them, right, you have to think about like, well, I might be interested in a different effect size for each of them, right? Yes. That's where probably the difference in power comes in, right? And the number of levels you have, of course, right? So if you have like 3 levels, you need more power than when you have 2 levels, probably, right?
Yeah, so with 3 levels, power will be lower than with 2.
So right, yeah, it will be lower, right?
Or more tasks.
And that's why you say like, hey, once you have multiple attributes and you're interested in all of them, you basically have to calculate. I think that's what you're saying here, right? The last thing is like, you have to figure out what's kind of like the minimum power, like what's the biggest kind of like effect size, the largest number of. So would you start with, I mean, you could say, well, I don't calculate, I mean, I'm thinking about efficiency, right? I look at where do I have the most levels and where do I think it's going to be the smallest effect size that I'm interested in, right? Would that be the starting point instead of like really calculating all of that?
Yeah, I mean, that would be a start. I mean, yes, if you just, I mean, let's put it this way. If you just want to loop this entire thing and you don't care how long your computer is calculating, I don't think there is any a priori reasons against not just calculating the whole thing. But yes, I mean, you could start with the one where you expect the lowest power to begin with. But there's also the question, are you really interested in this effect? I mean, sometimes, your main theoretical thrust lies in a certain attribute and its levels. You may just add other attributes to make sure that these things are accounted for. So randomized and therefore cognitively divorced from other levels where individuals may have an association about whatever hypothetical profile you're creating. So it really depends. But yes, I mean, you will probably have a strong a priori expectations about where an estimate of substantive interest is least powered. So starting with that one can probably speed this up. Yeah.
More often than not, if you add an additional attribute, you're probably then, even if it's not your primary one, you add it because you are interested in their interaction, right? So it makes stuff more complicated.
I think I have maybe a follow-up question on this. So when I look at like the results from conjoints, the levels of the attributes are ordered in some way, right? And so I don't actually care that like, whatever age 20, the effect is this, age 25, the effect is this, and no, I think I'm looking at the trend in the coefficients, right? I don't know how to implement that idea.
So what you're saying is within features, the levels are magnitude ordered and you're interested in.
So I'm just trying to think like the Heimler paper about like which elements are accepted, right? And you see, okay, so education different education levels, and the more educated they are, the more people like them.
Yeah.
But I mean, nobody actually ever goes and compares, between 2 individual levels. They just want to look at where that trend is good.
Yeah, I mean, so what you're saying is essentially the choice of the reference category is very arbitrary.
Okay, yeah, that's
so yeah. I mean, but it could be that you're interested in a specific pairwise difference, and it could also be that, I mean, in this case, education is an ordinal variable, so having a not necessarily linearly but monotonously increasing effect makes sense. But with other things like, I don't know, being a partisan of some party in a multi-party system, it could be all over the place. So, and then the choice of the reference category is even more arbitrary in a way, and you may want to compare, you know, the SPD versus the CDU supporter and the green versus the AFD supporter. So really starting with the pairwise first difference, which is the idea captured by a specific pairwise AMC, really makes sense.
So I just, it would just involve more judgment on your part, like on the part of the researcher, like what really is the thing that you want to. You have to pick one.
Absolutely, yeah, but that's also what I meant by, you know, subject this to your budget constraints. If you really do this for all pairwise comparisons, you will probably find something that requires a ridiculously large sample size, right? I mean, you will get a distribution, of course, and probably you just want to chop off the right-hand side tail and be like, okay, this is how much I'm willing to spend and not more, even if that means that there's, I don't know, 5% or so, or 10% of pairwise comparisons that may not be sufficiently powerful.
Okay, if there are no more questions right now, thanks again for your excellent presentation. This workshop concludes the fall series, and Alex will tell us which workshops or which sessions we will have in spring.
Yeah, we have an exciting lineup for the spring semester. So starting in February, continuing with conjoined experiments, actually we'll have Asia Magazini from the Hurley School coming. In March, we'll have Lydia Repke from MZES talking about developing and pretesting survey questions in the tool SQP survey quality prediction. And in April, we'll have two talks, Olga Kono-Nymkina from LMU Munich on using AI tools for research, and Carla Rohrwohl from Oxford University on sequence analysis. So stay tuned on more information about these events. Yeah, thanks again for coming, and yeah, see you soon.